Welcome to e-Pathshala lecture series in computer science, and this is a course in cloud computing. Today we will talk about concurrency in cloud. So, the learning objectives of this module is we will look at what is a transaction, we will see the acid properties of a transaction, and then we will see how or why transactions create a concurrency problem, and then we will look at the mechanisms of controlling such concurrent accesses. So, in the last class we discussed Chandy-Lampert's algorithm, global snapshot algorithm, and we looked at the major usages of this snapshot algorithm. This class we will look at concurrency. Let us do a recapitulation of what is a remote procedure call. Remote procedure call is a mechanism of communication, and where any two processes can communicate over the network in quite a similar manner as a local procedure call. So, a caller process is sitting in one machine, and the callee process or the call process will be in another machine, and these two processes can easily communicate with each other. So, this is the overall mechanism of RPC, where we see that process 1 is the caller process. There is one additional process that runs in both the machines, in each of the machines, that is called the stub. In the caller process, the client stub runs, and the process contacts only the stub in turn contacts the server stub contacts the callee process. Similarly, when it is time for the result to come through RPC, callee process sends the result only to the server stub transfers the data to the client stub delivers the data to the caller process. So, what are the communication semantics? We saw that there are three semantics. One is called the exactly ones. That means that whatever way I send as a sender, it is received as a receiver, no additional messages. Although we have looked at the communication, and we know that to make the communication happen, we need to retransmit, we need to duplicate messages, but as far as the higher level of communication is concerned, the senders and the receivers are concerned, if they demand an exactly ones semantic, it means that all the underlying mechanisms must take care of this fact that there should not be any reflection of the retransmissions and disturbed ordering. So, that is called an exactly ones. Sometimes or many times we really do not want to put so much of restriction. So, we say that okay, we are good with at least once. So, I will send a message, and your system will guarantee that it will be executed or it will be calculated at least once. So, I am allowing many more times to be executed, but I am demanding that ensure that one time it has been executed. So, that is a at least once protocol. If that is not what I desire, I may go for at most once, which is 0 or 1. That means do not worry about whether it is executed or not, but if it is executed, it should be executed only one time. There cannot be a duplicate execution. Depending on the kind of application that we are using, we can go for any one of these semantics. The underlying mechanism of RPC will implement these, and will use based on the specific application and the requirement, it will use the any specific semantic that is required. Since RPC mimics the behavior of LPC, LPC has only exactly ones. Because there are no failures in LPC, no communication over the network. So, therefore, it is very easy to see that it is only exactly ones automatically. Under failures in a distributed environment, it is very difficult for RPC to ensure that but it can be done at an expense. It becomes very expensive. The mechanism of communication becomes slow. Now, there are many failures that can happen. Let us look at the failures of RPC. Call request message can be dropped, a return message, a reply message may be dropped. The callee process fails before executing the function, and callee process fails after executing the function. For the called process, it is very difficult to distinguish between these 4 failures. It looks identical. The result effect of these failures is identical to the called process. So, the function, if it is executed many more times, it may cause a serious problem. Imagine a bank account and you are debiting or crediting some money, and it gets executed many more times. Definitely there will be someone who will be very unhappy about it and not an acceptable situation. So, why we are worrying about RPC? Because a transaction extensively uses RPC. So, what is a transaction? Transaction is a series of operations between 2 processes or more than 2 processes, and the characteristic of a transaction is that it will be all these individual operations together will form one transaction, and that will give one specific result. So, the characteristic of the transaction is that although there are many operations in one transaction, all the operations must be executed or none of the operations should be executed. There cannot be an intermediate state in a transaction. If a transaction is difficult, a distributed transaction is one where the different processes are geographically dispersed. So, here is an example of transaction. T1 is a transaction. If we look at the transaction, we see that there is a server read, and so the data comes from the server, and then there is an if statement which increments or decrements the value of the seat, or it prints something and it writes back. In case there is a change, it writes back. Another example is where there is a read, and after reading the data is changed, and based on what is happening in this change, another read is happening and another change is happening, and the value is going back to the server. So, where are RPC here? There is an RPC here in this read, there is an RPC here in this write, there is an RPC here in this read, and in this write. So, more than one RPCs are involved in one single transaction or in one set of transactions. Now, transactions have to follow ACID properties. Let us look at the ACID properties. It's basically an acronym. A stands for atomic. Atomic says all the operations or none. C stands for consistent. The results will be valid. So, if it is making some partial modifications through the each of its operations, ultimately finally there should be a valid result. Isolated, if there are more than one transactions happening together, then each transaction should be in an isolated manner. One transaction should not interfere with the other transaction, and durable, once the transaction has made the changes, it should not be disturbed, that the result will be permanent. So, ACID properties of transactions cannot be violated. If it is a transaction, there will be ACID properties, and all these properties have to be maintained. The major problem comes in concurrent transactions. So, two transactions are executing two different processes accessing the same data object, and therefore, both of them are trying to make some changes in the data object, and this will cause a problem in the consistency part of it. These are concurrent transactions, concurrent accesses, and the solution to this is called the concurrent concurrency solution. Three well-known problems may occur. One is called a lost update problem, inconsistent retrieval problem, and incorrect read problem. Let us look at this. So, we will use this as an example. There are two transactions. One client in Delhi, it is doing this, it is looking at the value of marks, and the value of marks is in a server in Mumbai, and it is doing something and writing back. If this executes, it reads the value of 10, and if the marks is less than 100, then marks is marks plus 10, which makes the marks 20, and it writes back to the server. The other transaction does the same thing. It starts after the first transaction, it reads, now the value is 20, it reads 20, it checks it is less than 100, and it increments and writes back to the server. So, the value of the server will be 30, and then both the transactions commit. There is no problem if these two transactions are accessing the same data, because one is completing and then only the next one is starting. Now, a lost update problem happens if they execute like this. This client 1 reads the data, so marks 10 has come, and then the client 2 starts concurrently and it reads the data, the value will be 10. Now, the client 1 executes its calculations, and its marks in its own machine becomes 20, and it writes back. So, now the value of the marks is 20, but if this Chennai client continues, then it executes this instruction on the marks that have been brought by it, which is 10, and it again says marks is marks plus 10, which is 20, and it writes back. So, it overrides the earlier 20 and it does not make any changes. Therefore, this is a wrong transaction. This is a lost update problem. So, the update by the earlier transaction is lost by the next update. The next problem is called inconsistent retrieval problem. Here, the marks, let's assume the marks is 90, and we execute the same client on marks 90. So, it reads the value of 90. This also reads and gets a value of 90. Now, it makes a change and the value becomes 100 because it adds, and then it writes the server. So, the server at this point in time will be 100, but this Chennai server continues to check whether marks is less than 100 or not, and it finds that marks is less than 100 indeed, and it prints that marks is less than 100 at a point in time where actually the marks is 100 in the server. So, therefore, it is incorrect. So, this is wrong. A inconsistent read problem says that if marks is marks plus 10 and it writes marks 20, and then it says marks is marks plus 10 and it writes 30, then if the first client aborts, if it aborts, then the value of marks should go back to 10, and this Chennai server should have made it 20, but we have made it 30 and that is wrong. So, this is called an inconsistent read problem. So, how does one solve the inconsistent read problem is by creating a serial equivalence. A serial equivalence of what? That is what we will see. If the transactions are executing one after the other and neither then none of the problems will occur. So, the interleaving of transaction is causing the problem. So, does it mean that we cannot interleave at all? That is not correct. There is a mechanism of doing a correct interleaving, and we have to find a correct interleaving of all the transactions. And this correct interleaving is called a serially equivalent interleaving, which is the same as if one transaction completes and then only the other transaction starts. So, why don't we allow that to happen rather than trying to interleave? Is because then everything will be very slow. Interleaving is done to make things faster, and it is important. So, the use of serial equivalence as a criteria for correct concurrent execution prevents the occurrence of lost updates and inconsistent retrieval problems. So, the lost update problem has occurred because the transaction was reading a old value, and if we do not allow the transaction to read the old value, that means if the transaction does not quickly allow the other, if the object does not quickly allow the other transaction to read, then this problem will not happen. Similarly, inconsistent retrieval also occurs when the retrieval happens before or after the update operation. It cannot occur if the retrieval happens before or after the update transaction. So, how do we implement ACID? We have to take each property and ensure that that property is implemented. So, implementing atomicity is something that we will discuss in the next module. We will talk about a solution for durability. It is very simple to ensure durability. Whenever a transaction has completed, we put it in a stable storage, and therefore ensure that the result is durable. The solution for isolation and consistency is the discussion. It ensures that a transaction in progress does not interfere with another transaction in progress, so that there is no concurrent access of data. So, how do we implement this? The easiest way is to log. The question comes, what to log? We log the shared data for every transaction. If there is a data that is being shared by multiple transactions, we put a log onto it. If one transaction is in progress, the other transaction will not be permitted. Do we actually need so much of restriction? We can look at the individual operations and see that which operations are to be logged, and then execute logs. So, we have two operations, one is called a read and the other is called the write. These are the two operations, the RPC based operations, which are to be restricted. So, how do we use log? We use log like this. If client 1 starts first, it puts a log on this data, which is the marks in the server, and then when client 2 tries to access, it is not allowed. It will be asked to wait, and client 1 continues. Client 1 makes the marks to its correct value, and then when client 1 unlocks, then the client 2, which will be waiting on this marks, will be given a go ahead and continue. So, then all the problems will be resolved. So, how do we implement log? Do we execute all reads and writes to be logged? It is not really required. Certain combinations alone are problematic combinations. A read and write on the same data, write and read on the same data, and write and write on the same data. A read and read on the same data is not a problem. A read and write on two different data also is not a problem. So, all reads and writes need not be stopped. We need to identify the specific reads and writes that are causing a problem, and these operations are logged. So, we call them conflicting operations, and these conflicting operations should come under log. We call the data object as an object, and each object we provide with the ability to log the object. At any point in time, only one transaction is allowed to put a log. So, other transactions will wait and will be given the access only after the first transaction has before we write or read, we acquire, before the writing or reading process happens, we have to acquire a log. If there is a conflicting transactions, then conflicting operations, then the data object will not allow the log to be obtained. After acquiring a log, the transaction T can perform all its reads and writes multiple times. There is no problem in accessing the same data multiple times once we have one log. and then when it unlocks, we the other waiting transactions, one of the other waiting transactions will be allowed. So, we have two types of lock. One is a read lock. Read locks are also called non-exclusive locks because two reads on the same data object by two different transactions will be allowed. And then we have write locks. Write locks are called exclusive locks because one write lock will stop all other read and write locks on that same object. Multiple non-exclusive locks can be allowed, but only one exclusive mode lock will be allowed. So, this is the table where we see that read and write, read and read are a tick, which means that a read can be used along with a read, but all other combinations are not allowed. So, let us look at an example. We have three transactions T1, T2 and T3, and we have one data object O, and if the transaction T1 is asking for a read lock, it will be granted because no lock is there. If now the transaction T2 asks for a read lock, it will be granted. Similarly, if transaction T3 is asking for a read lock, it will be granted. This is what a non-exclusive lock is. So, any number of transactions can acquire lock. An exclusive mode lock, if transaction T1 has asked for a write lock, first time it will be granted. If now transaction T2 is asking for a write lock, it will be asked to wait, and similarly transaction T3 is asking for a write lock, it will be asked to wait. Now, what happens if there are mixed modes? Let us look at this. Transaction T2 is asking for a write lock, it will be granted, of course, because this is the first time. Transaction T1 is asking for a read lock, but on top of a write nothing will be allowed, so it will be asked to wait. If transaction T3 is asking for a write lock, then also it will be asked to wait. What is the process of unlock? Every time a transaction has acquired a lock, it has to unlock at the end of the work. On receiving this, the pending work will be allowed. Now, there is a special case. Assume that some transaction T1 already holds a lock. Is it possible to grant another type of lock to T1? So, T1 is holding a non-exclusive mode lock. Is it possible to acquire an exclusive mode lock? Yes, it is possible if during the exclusive mode lock we have not allowed other non-exclusive mode lock to be implemented. So, one read is happening. If no other transaction has asked for a read, then a write by that same transaction will be allowed, but it will not be allowed if some other read is happening. The read two transactions are reading, then T1 cannot ask for a write lock. So, what are the problems? The problem again is that if there is not a specific schedule properly done, it causes deadlocks, it causes performance degradation, etc. So, schedule is a list of operations ordered by the time of concurrent transactions, and a correct schedule must possess two specific characteristics. One is that it is a legal schedule, it has not granted any conflicting locks, and it is serializable. What is a serializability? It has an equivalent serial schedule, which without going for concurrency, as if we had implemented or executed transactions on their own. So, let us look at the problems of locking. If we have the transaction T1 is acquiring lock X and unlocking it, and then acquiring a write lock X and then reading Y and then executing something and writing Y. Similarly, transaction T2 has a read lock X and reading Y and unlocking, acquiring a write lock. It is also getting a read lock and doing X equals to X plus Y and acquiring a write lock and writing on, or already acquired a write lock, so writing on X and unlocking X. So, the initial values of X is 20 and Y is 30. If we have a serial execution order for T1 followed by T2, then the value of x will be 50, y will be 80. If the order is interchanged, T2 followed by T1, then the value of x at the end of it will be 70 and y will be 50. But there is a schedule. First we acquire the logs of x, and then we allow T2 to execute, and then we allow T1 to continue the rest of it. We see that with the initial value of x equals to 20 and y equals to 30, x becomes 50 and y also becomes 50 by this schedule. So, this is a schedule that cannot be, it is not a serializable schedule, it does not have a it does not possess serializability. So, to avoid this problem, we allow two-phase locking protocol, which does not let this problem to happen in locking. Each transaction is executed in two phases. One is the growing phase, where the transaction will obtain the logs, and the other is the shrinking phase, when the transactions will release the logs. And the point where the growing phase stops and the shrinking phase starts is called the lock point. So, this is a example where it is growing, it is acquiring all the logs, and then a lock point comes, and then it has to release all the logs. So, this is a two-phase locking protocol. A transaction cannot acquire lock once it has started releasing. So, all acquiring will happen in one phase and all releasing will happen in the other phase. The properties of 2PL are that it guarantees a conflict serializable schedule. There is no conflict in a schedule created by a two-phase locking mechanism. However, it may cause a cascading abort. If we abort one after releasing a lock, if we abort one transaction, it may cause many more transactions which are part of the two-phase locking protocol to abort. So, to summarize our this discussion, we started with an overview of RPC. We saw that a remote procedure call is a mechanism which very extensively in a distributed environment we use to make two processes communicate with each other. The reason why RPC is so popular is because it follows LPC, and this LPC is very simple and people are very used to it. So, being able to use an LPC like mechanism makes things simpler. We looked at a transaction, we saw how transactions work, and we saw the properties of transaction, acid properties of transaction, and we looked at the issues of isolation and consistency in the transaction. And then we moved forward and we looked at the solution for concurrency control, concurrency access control is that a locking mechanism. So, in terms of that, we looked at a specific locking mechanism. Generally, putting a lock is difficult because finding the correct schedule is not easy. So, we looked at one specific such protocol, which is called a two-phase locking protocol, and we saw that no problem will arise if there is a two-phase locking protocol. In the next class, we left something in this class, which is the atomicity. We did not look at how to control concurrent accesses and still maintain atomicity of transactions, and we will see how atomicity is ensured in a distributed transaction, and we will see the atomic commit protocols. In that, we will look at one specific commit protocol called the two-phase commit protocol. These are our references. Thank you.